Let me provide a little bit of structures into what we have already learned so far from things that Jack has presented, and also I mentioned briefly. One of the foundations of behavioral economics is this one: prospect theory and reference-dependent preferences. So this, which gives us things that we learn, that we know about loss aversions and other related stuff. So let me go into a bit more detail on this and a bit of background of what we do in economics. We taught this prospect theory and reference-dependent preferences. I was talking to some of you, and I know that your background varies a lot. Some of you come from political science, from urban planning, some of you from economics, so your background in economics may differ from one another. So it's good to have a little bit of refresher of what we learned in economics, okay? So let me start by giving an introduction. So this is about how people make decisions when facing risk and uncertainty. Okay? So let me just be very briefly. Suppose that you are an event manager and you are planning an outdoor sport event. Because it is outdoor, it depends a lot on the weather, whether it's going to rain or whether it's not going to rain. So you need to have some kind of estimates on the likelihood that the rain will come and the likelihood that the rains will not come. Okay? So suppose you have some basic calculations and you find out that the probability of rain tomorrow is 30%, meaning that there's no rain with 70% chance. Now, if it does not rain, you can have this outdoor sport event. Your estimate is that suppose you will make $5,000, Singapore dollars here, not Taiwanese dollars. But if it rains, too bad, because it's outdoor, not many people will come, so you only make $1,000. Okay? Now, of course, you can calculate the expected value. With 70% chance you get 5,000, with 30% chance you get 1,000. So the expected value of having this outdoor sport event is $3,800. Now, suppose you have an alternative. Instead of having it in outdoor stadiums, you can have it in an indoor stadium. And of course, because it's indoor, you are not going to be affected by the weather. And you get sure payout from that. So your income, suppose, is $2,000. So how are you going to make decision here? Whether you will have the sport event in outdoor location or in indoor. So what kind of criteria that economists use to decide what to do in this kind of situation? So people might be tempted to use expected value comparison. That is, 3,800 if I have it in the indoor stadiums, and 2,000 if I have it in outdoor stadiums. People might see, oh, yeah, so 3,800 if it is in outdoor and 2,000 if it is indoor. So people might say, oh, then in that case, I'll go with outdoor. Is that the correct way of making decisions? Can you make your decision based on the expected value? The answer is no. Economists will say, no, you cannot just compare expected value. Okay? So it depends on what? People are different in terms their willingness to take risk. Okay? Some people are more risk-seeking than others. So if you are more risk-seeking, then I'll prepare to get the chance of getting rain, so I'll have it outdoor. But some others are more risk-averse. So they are very careful. They say, no, I'm not going to have it because there is rain coming, possibly. So I will not do it, even though the expected value is 3,800. Okay? So it depends very much on risk attitude. So that's why the way economists see when we have this decision making under risk and uncertainty is looking at something else rather than comparing the expected value. Okay? So there is a problem when we compare the expected value. So let me give you another example. How many of you have heard about something called St. Petersburg paradox? So let me explain. It's a very simple game. You flip a coin repeatedly until the goal is a tail first appears. So the pot, the price starts with $1. And it doubles every time head appears instead of tail. So every time you get heads, the play goes on and the pot doubles. Okay? So you will win whatever is in the pot the first time you get a tail. So when tails comes out, that's the end of the game, and you get whatever amount of money in the pot. Okay? Now, of course, you can calculate the chance of getting tail on the first toss. You get $1. And if you get tail on the second toss, you get $2. If you get tail on the third toss, you get $4. If you get tails on the fourth toss, you get $8, and so on. Because it can goes on and on and on, unless you get tail when the game stops. Now suppose I tell you what, I ask you to choose. I gave you $10 for sure. Now I have money, I give you $10, 10 Singapore dollars. Or I let you play these St. Petersburg games against me. What will you choose? What will you choose? Which one would you choose? Most people would say, give me $10 for sure, I'll get $10. And this is why you cannot use expected value, because if you calculate the expected value of the St. Petersburg paradox, the St. Petersburg game, what do you find out? The expected value is infinite. Okay? You have an infinite sequence, potentially, with a probability of 1/2 every time that you end up with tail. Okay? So that's what happened. So if you use expected value, you should always choose this St. Petersburg game. But people don't. People prefer $10 rather than playing this game. So that's why we cannot use expected value to compare between options. Economists come up with something called expected utility. So that is, this is due to Daniel Bernoulli, the value of a gamble is actually not the monetary value of that gamble, but rather it should be some subjective value, or economists would call it utility, okay, that people attach to this monetary value. What do we use with the money? We use money, we buy stuffs, we buy goods, we consume goods, we derive utility from the consumption. That's what economists value, rather than the money in itself. Okay? So the utility of $1 is essentially the amount of the satisfaction you get from consuming this $1, buying goods with this $1. So that's the expected utility, the utility that we have. So what people do, people maximize expected utility. Okay? Now, then there are many other examples showing that people don't do based on the expected value, like these gambles, for example. Option A, you are offered a gift. You get 80% chance to win $100 and 20% chance to win nothing. Option B, you are offered a gift. You get $80 for sure. So when you ask people to choose this, which one would they choose? If you calculate the expected value of A is 82, expected value of B is 80. So if you are basing on the expected value, you choose A. But most people, almost everybody, would pick the sure thing. That is option B rather than the gamble option A. So if evaluation is based on expected value, option A should have been chosen. So that shows that we don't use expected value. We maximize expected utility. So that's why, if suppose there are two possible outcomes, outcome 1, rains, outcome 2, no rains, the expected utility is equals to the probability that rains happens and the utility I derive when the, rains happens, and I get the payoff because of that kind of situations. Same thing also for the second outcome. That is your expected utility. Okay? So whether people are willing to take risks or not depends very much on the shape of these utility functions. Okay, so that shape of the utility functions determines whether you are risk averse, whether you are risk seeking, or whether you are risk neutral. Okay, so if you have something like this, linear, your utility function is linear, so you are risk neutral. Suppose there are two options, one option gave 10, the other option gave 30, with 50% chance, the expected value is equals to 20. So if you have to choose between getting $20 for sure or playing a gamble that gave you 10 or 30 with 50% chance with expected value of equals to 20, you are going to be indifferent between taking the gamble or not taking the gamble. So you are said to be risk neutral. Okay? Now, if your utility function is concave, like this, where this is the amount of money that you have, and that's the utility that you have, if someone gives you two options, $20 for sure, or a lottery, you might get 10, you might get 30, with 50% chance, the expected value is at 20. So if you are that person, this getting it for sure give you D. Okay? The combination, linear combination between 10 and 30, that's basically is this dotted line. You give you F. So you prefer D because that gives you the higher utility than F. So if you are this person, basically you're saying between the choice of $20 for sure or playing the gamble that can potentially give me an expected value of money, $20, I'm going to take the sure thing. I don't like gamble. Okay? So that's risk averse individuals when your utility function is concave. The last one is if your utility function is convex. So in this case, it's the opposite. Between $20 for sure or a gamble that can give me 10 or 30 with 50% chance, I will always pick the gamble. I'm willing to gamble rather than getting sure money of $20. So this shows that this person with this utility function is a risk seeker, willing to gamble rather than take the sure payoff. So people are different. People have different risk attitudes. Some people are more risk seeking than others. So in reality, it's not as straightforward like that. So we are not always risk-seeking. We are not always risk-averse. Depends. For example, very often we see that people exhibit both risk-seeking behavior and risk-averse behavior at the same time. So for example, I have home insurance, but sometimes I buy 3D lottery. So buying lottery, meaning that I'm willing to take risk. Getting home insurance, meaning I'm worried that I might get something with my home, so I'll buy insurance. Okay? So we also often risk neutral or even risk seeking when it's about a small amount of money, small gambles. We don't really care much about small gambles, so I'm willing to take risk because the consequences is small. But when it relates to something that is big, has a big consequences, I would tend to be more risk averse. Okay? So in order to be able to represent all this using utility functions, this is a little bit of a background, some basic microeconomics here. So preferences that underlie these utility functions must satisfy a set of axioms. Okay, so I'll go into, it's seemingly a bit technical, but I'll try to explain it intuitively. What does it mean? And I see where do we have when we see the things that we observe from people when they make decisions. Okay, so the first one is completeness. So if you have 3 lotteries, A, B, and C, you can always say whether you prefer A to B or prefer B to A, or you are indifferent between A to B. Okay? So transitivity means that if you prefer A to B, and you prefer B to C, you will prefer A to C. And continuity means if you have 3 lottery A, B, and C, and you prefer A to B and B to C, then you can construct a probability P such that if you combine lottery A and lottery C, you will be indifferent with lottery B. So let me explain a bit. Continuity. So let me give you an example. Suppose that there are 3 outcomes. The first one, you get $1 million. Remember that? Second, you get nothing. The third one, you die. Okay, there are 3 options here. I can construct a lottery, 3 lotteries in fact, using these 3 outcomes. So I call it A, B, and C. So what is my lottery A? Lottery A says that I have 2/3 chance of getting $1 million. With 1/3 chance I get nothing. But I will not die. 0, not die. 2/3 chance of getting $1 million. Lottery B, I will not get $1 million. That means for sure I get nothing, but I will not die. Option C, I'll die for sure. So I don't get $1 million, I don't get nothing because I died. Okay? So if I ask you to rank A, B, and C, which one would you prefer the most? Obviously A. I prefer to have some chance of getting $1 million and not dying. And that's better than getting nothing and not dying. And that's better than dying. Okay? So the option is A is preferred to B and B is preferred to C. Now, let me construct a new lottery A prime. I throw in probability of getting lottery A and the remaining probability of getting lottery C. So what does it mean? Essentially, I say, let me give you this lottery where you can have the chance of getting $1 million with a little bit chance of dying. Okay? And I ask you whether which one you prefer, A prime or B. B, for sure you not get $1 million, but you don't die. A prime, you might get $1 million, but with some probability of dying. It's not impossible to find the value of probability such that this lottery A prime would be at least preferred to B. Okay, that's the continuity axioms. Okay, so that is the continuity. So as long as the probability of dying is not sufficiently large, you might have that kind of situation. That's the meaning of the axiom continuity. What about the independence? So independence says that if we mix 2 lotteries with a third one, so the preference ordering of the 2 mixture will not change. And this axiom is very often violated from countless experiments. Okay? So essentially it says that if you prefer lottery A to lottery B, then if you throw in C to the left hand side with some probability and throw in C to the right hand side with some probability, this preference ordering don't change. You throw in something to the left and to the right, doesn't change your preference between this and that. Okay? In words, it means if you add some positive risk of death to the chance of getting $1 million, and you compare that to some chance of death to getting nothing, you will still prefer this. Same amount of probability of dying, I would prefer to have a chance of getting $1 million. That's the meaning of independent axioms. Okay? So that preference relations don't change if you throw something C in this case. So if you have all these axioms satisfied, you can construct the utility functions, and then you can use the one that I have shown earlier. If there are two outcomes, you have probability of outcome 1 times the utility of outcomes 2, and so on. So there could be many more than just two outcomes. Okay? So the overall utility of a prospect is the expected utility if it's all outcomes. Okay? So that's the basic foundation of expected utility theory. So gambles or lottery are going to be evaluated by integrating. You don't look gains and losses separately, you combine gains and losses. Okay? So that's the meaning of asset integration here. So let's evaluate whether this is satisfied in real world. Okay? Let me give you this. This is an experiment by Kahneman and Tversky in 1974. Suppose you are asked to choose between the followings. The variant of this was shown by Jack earlier. In addition to whatever you have owned, you are given $1,000. Someone gave you $1,000. Okay? And then you are asked to choose between option A or option B. In option A, you have the chance of getting another $1,000 with 50% chance. Meaning that with 15% chance remaining, you get nothing. You stay with $1,000. So you either get 1,500 or 1,000. Okay? Or option B, you get 500 for sure. The expected value of this is 500, and that is 500 for sure. So the expected value of taking option A is 1,500. The expected value of taking option B is also 1,500. So which one would you choose? You've seen from Jack's earlier example that in this case you choose which one? You will choose B. Okay? Because in these kind of situations, you prefer to get 500 for sure rather than the gambling, and there is a chance that you might not get anything. Now, if I change the problem, suppose that I give you $2,000. Why I give you $2,000? Because I want to make these two problems exactly equivalent. I ask you to choose between C and D. If you take C, there's a chance that you lose $1,000 with 50% chance. So from 2,000, you lose 1,000, you get only 1,000, or you might not lose anything. Okay? Or option D, you lose $500 for sure. In terms of expected value, it's the same. 1,500, 1,500. If I give you these two options, what would you choose? Most people choose C in this loss frame. I'm willing to gamble for this because there is a chance that I might not lose anything. But this violates the expected utility theory. Why? Given the same utility functions, your utility function don't change. If you face this and if you choose this, because your utility function remains the same, you should also choose this. But what we see, people switch in terms of their choices. Here, people choose certainty. Here, people choose gamble. So something wrong here. This doesn't come from the expected utility theory, because it cannot be explained. Your behavior has to be consistent. That's what we give, what will lead us to prospect theory. It turns out, implication of this is that people treat gains and losses differently. People feel differently about gains and losses. When they face gains, they become risk-averse. But when they face losses, they become risk-seeking. They take risks because there is a chance that there might not be any loss. Okay? So that's why we need to have a new paradigms to explain that. So by the way, this is the result, just like what you have told me verbally. So most people choose this, and here most people choose that. Okay? So people treat gains and losses separately. So people are risk-averse in gains, and they are risk-seeking in losses. Why do they are risk-seeking in losses? Because they are loss-averse. So don't mix up this. Loss-averse, because I'm loss-averse, so I want to get rid of losses. How do I get rid of losses? By taking more risk. Okay? So that's where we have a loss aversion come in. So the utility of losing is larger than the utility of gaining. People always want to overturn losses. And this explains all this kind of behavioral. The example that Jack mentions, car, buying car in Singapore. To be more specific, in Singapore there is a policy called certificate of entitlement. If you get a car, you are not only buying the car price, you are not buying the road tax and all these things, but you also need to buy for the license. And the license is in fixed supply, decided by the government, and the price is determined through auctions, depending on the number of buyers who wants to get a car. If there are more buyers, then the number of license price will go up. When there are not many buyers, price will go down. So it's a market mechanism. Okay? So if happens to be that the COE price says so much, and I buy the car anyway, to me, as an economist, I should treat that as a sunk cost. I should forget about it, because that's part of the deal I have to make when I buy the car. But people cannot avoid thinking that that is something big that I incurred in the first place. So what do? COE, by the way, the policy objective is to reduce congestion. And to reduce congestion meaning to reduce pollution as well, clean air. But because of this sunk cost fallacy, because of this loss aversion, I already paid a lot. So I better drive more often. That's why Jack mentions that the kilometers, the amounts that people drive in Singapore is really high because of this sunk cost effect. I cannot shake out that I pay so much, I better make use of the car so that it's worth it. So I drive more often. Another policy in Singapore, if you go to the casino, I don't know whether there are casinos here also or not. No, in Singapore there are two places. One is Resort World Sentosa and the other one is in Marina Bay Sands Hotel. You know that if you are Singaporean or if you are permanent residents, just like me, if I go there, I need to pay $100 entrance fee. If you are foreigners, you don't have to pay. So you don't have to pay to go to the casino. But think for a while. Suppose I enter and I decided to pay $100. That's always in my mind. Then I'll start thinking, oh, I pay $100. How do I get rid of this $100? How do I get rid of this $100? It induced me to be more willing to try on to gamble, because I want to recoup back the $100 that I have already paid. Okay? That's also loss aversion because of that. Okay? So there are many examples, many applications of loss aversions, which I cannot go into all of this, but there are a lot of examples on that. And for policymakers, always remember that people treat losses and gains differently. So you might want to tailor your policy using this framing, gains and loss framing. Okay. Now, let's go into the violation of expected utility theory more. There's something called RA paradox. I don't know whether you have heard about this, but this experiment shows a violation of independence axioms. Okay, so consider the following options. I'll ask you to choose. Option A, you have 98% chance of getting $500 million. A lot of money. With 2% chance, you get nothing. Option B, you get $100 million for sure. Which one will you choose? So what about the following options? Option C, with 0.98% chance, you get $100 million. That means with remaining 99.02% chance, you get nothing. Option D, with 1% chance, you get $100 million. With 99% chance, you get nothing, zero. Which one will you choose? C? Who choose C? Most people choose C. Most people indeed choose B for the first one, choose C here. Now, if you see this pattern of choice, this is a violation of expected utility theorem, the independence axioms in particular. How do we see that? Okay, let me show it to you. So that's the second problem. That's the second option here, C and D. So I write it back there. Okay? And I'm going to rewrite this second problem into this. It's exactly the same. 0.98% chance of getting 500 millions. I split it into 0.02% chance of getting 0 and 99% chance of getting 0. It's exactly identical as that. Okay? Now, focus on these two and on this. And that is the first problem, option A and option B. 98% chance of 500 million, 2% chance of 0, and $100 million with 100% chance for sure. What do you see between C and D here and that? This pair is constructed using this. You throw in a probability of option C. So that second problem, this one here, is the same as saying you have 1% chance of getting this. If you have 1% chance of getting this, you have exactly that. Okay? So the second problem is exactly the same as 1% chance of reaching the first problem. So that is something like this. So they both are the same, but you construct it. You remember in the independence axioms, you throw in C on the left-hand side, you throw in C on the right-hand side with a mixture of probability, your preference would be remains the same. So this, because you switch, you reverse, is a violation of the independence axioms of the expected utility theory. Okay? So you see that the expected utility theory doesn't really work in practice, because by looking at people's choices, their choices actually violate the very basic principle of the axioms of expected utility theory. The question is, how can you use the expected utility theory to be based on how people make decisions? Okay? So that's the independent axioms that I just mentioned earlier. So there are more examples. This example shows something called certainty effect. Let me ask you to choose. Option A, 80% chance of getting $4,000. With 20% chance, you get nothing. Or getting $3,000 for sure. Which one? B. Most people choose B. What about this? 20% chance of getting 4,000. 20% chance of getting 3,000. Who choose C? So most people, I heard people say C. So indeed, here, most people choose B. Here, most people choose C. This is also a violation of the expected utility theorem. Why? Because this A, B, and C, D are exactly identical. So C, D here, you just divide everything by 4 there, the probability. 80% divided by 4, you get 20%. 100% here divided by 4, you get 25%. Exactly identical. But the choices switch. So why is it so? And that's interesting. Because when this probability is large, you are not talking about something that is very little chance of happening, but something that is has a good chance of happening. Here, 20% and 25%, they don't really look different or sound different to you. So here, you focus more on the difference in probability. 100% and 80%, that's big. Here, you don't focus on the difference between 20% and 25%. You focus on the amount of money, 4,000 and 3,000. 4,000 is more than 3,000. 20% is not really that different from 25%. Okay? So that's violations and some more. And I'll go very quickly on this. Option A, 50% chance to win 3 weeks tour of Europe, or a 1 week tour of Europe for sure. Most people, what about this? 5% chance to win 3 week tour of Europe, or 10% chance to win 1 week tour of Europe. Most people will do exactly like what I say here. Okay? So if you prefer B to A, according to expected utility theory, you should also prefer D to C. Okay? So there are many more like this. Which one here? Most people choose B. Here, most people choose C. Option A and B, probability of winning are large. This is the same reasoning that I mentioned earlier. So people choose option that is more probable. And this one is small, so people choose the gains, which is larger. Okay? So this is something called possibility and probability effects. So there are more. I'll just go very quickly here. So this is all the reversal of choices. Violation of the expected utility theorem. Okay? So, first lesson we learned. People don't combine gains and losses. People actually treat gains and losses separately, and people behave differently towards gains and towards losses. People are loss averse, and that's why people become more. Why suddenly change? Okay, so that's the first things that we learn. Second, in prospect theory, reference points matters. Okay, so people evaluate a prospect based on a reference point. So let me give you an example. This example, Jack is here. Jill is somebody else. Jack and Jill each have a wealth of $5 million. Okay, and they have the same utility functions. Assumes that they are identical. Yesterday, Jack had $1 million, but Jill had $9 million. So do they have the same utility? Are they equally happy? They have the same utility functions. So if you use expected utility, what matters is what do you get? You get $5 million now, and Jack 5 million, Jill also 5 million. It's the same. But are they equally happy?
No.
No. Why? Who is unhappy? Jill is unhappy because before it's $9 million, now becomes only $5 million. Okay? So under expected utility theory, they should be equally happy today, the same wealth. Okay? So it's obvious that Jack would be happier than Jill. So reference points is important. That's the second thing from prospect theory. Okay? So another example that I typically would like to give is, suppose that you work all in the same company. So one day your boss call you, one of you, and tell you, I'm going to raise your salary by 20%. Are you happy? Very happy. Very happy. But what if later you, after you talk to me, you find out from the rest of your colleagues that they all get 40% salary increase? Will you still be happy? No. So even though you have a salary increase, that salary increase feels like a loss because you compare to the reference point. So that's the second point in prospect theory. So that reference points matters a lot. So another example, this I like to give to my students. You know, in Singapore, there is a grade point average system from 0 to 5. So if you are 4.5 to 5, you get first class honor, so highest distinction or something like that. Now, how do people use 4.5 as a cutoff? Is it from thorough study that 4.5 is the optimal one to decide whether one has to be first class or second class? No, it's arbitrary. But imagine, suppose there are two individuals. So person A has a GPA of 4.51. Person 2 has a GPA of 4.49. Do you think that they are intellectually different? No, they are possibly equally capable. They are just different by a little bit. But think, which one will have more incentive to study harder? The one that is 4.49, because there is still a target, a goal that the person needs to reach. 4.51, I'm already there. It's good. I need to study, but I'm already there. So these reference points matters because you are still below the reference point. You need to work harder. So because you want to avoid, you are in the loss domain. So you want to get rid of that losses. So if you are already high, you are in the gains domains. You are not going to do a lot of much things. Okay. So that's the importance of reference point. Then the last part, I should talk until 12:30. So I'll take more around 15 minutes more, and then I'll give it to Jack. Okay. So two things that we learned. First, gains and loss, the attitude different. Second, reference point. The third one is decision weight. So let me explain intuitively what decision weight is. Okay. So let me ask you, suppose you have 10% chance of getting $1,000. And then that chance increased to 20%. From 10% to 20% chance of getting $1,000. Compare that situations to if at the beginning you have 90% chance of getting $1,000 and that chance increased to 100% chance of getting $1,000. The amount in terms of the difference in probability is the same, 10%, 10%. But do you value these two equally? No, because from 10 to 20 doesn't really give you a much stronger feeling. But from 90 to 100, that's a big thing because it becomes certain you get $1,000. So that's the importance of the decision weight. So depending on where you are in terms of probability, you put different weight to that. Okay, so the best example is this one. This one is something called Russian roulette. Do you know what is Russian roulette? It's a roulette game, but it's a very dangerous game. So you have a gun. So in a gun you have 6 chambers of bullets. Okay, so suppose you are forced to play a Russian roulette. So the gun is loaded with 6 bullets. You are given the opportunity to pay for the removal of 1 bullet from this loaded gun. Okay, question is, would you pay as much as to reduce the number of bullets from 4 to 3? If initially there are 4 bullets, it reduced by 1 into 3. As you would reduce the number of bullets from 1 to 0. Which one you will be happier to have? From 1 to 0, of course. What about this? Removal of 1 bullet from 4 to 3, or removal of 1 bullet from 6 to 5? 6 to 5, 6, for sure you will die. 5, there is still a bit of chance that you might survive. So you of course value 6 to 5 more than valuing 4 to 3. Anyway, with 4 you might die, with 3 you also might die. So it doesn't make any difference to you. Okay? So removing 1 bullet from 4 is not really an improvement from removing the only bullet in the gun. So, or removing 1 bullet when all chambers are loaded. Okay? So, in other words, changing the probability of an occurrence of an event from 3/6 to 4/6 will have a smaller impact on the value of the prospects than changing them from 0 to 1/6 or from 5/6 to certainty. So it suggests that you have some kind of a weighting functions. That's where the probability weighting functions come in. So it suggests that it must be, the shape must be concave near 0, small probability, and convex near 1. Okay? So it should be something like this. That's for small probability event. That's for the large probability event. So it's steeper because it has more impact. That's steeper also there. Here in the middle is flat. So that's the associated weight. And that's the probability from 0 to 1. Okay? So that's the 45-degree lines. That's when we get into the expected utility because the probability that enters linearly. Okay? Here we have a functions, which is this one here. So what is the implication of this? It has a lot of implication. Also for environment, environmental economics. Small probability events very often get exaggerated. People worry so much for some things that might have very little chance of happening. What would be a good example? Nuclear power plant. What is the chance of having a nuclear disaster? Very, very small. Okay? But it gets overweighted because people are worried that because it is a small probability event, if it happens, it can be catastrophic. But the chance of that happening is so small. And the question is, should we worry? Or should we not worry? Okay? So prospect theory tells us that for things like this, which has a very little chance of happening, very often people care a lot. So much. A good example in Singapore was that if you travel to Singapore using MRT, many years ago, there was no barriers between the platforms and the track. Okay? And there was one episode, sad case. There was a tourist coming from Thailand, and happens to be that she fell onto the track, and there is an onrushing train coming in. She survived, but she became disabled. And then because of that, everyone say, oh, this is so dangerous. So this is very dangerous. So this, but think for a while, how many cases like that happens? Very, very small chance of happening. But what happens after that? Government invested a lot to build the barriers. I mean, well, the barriers is useful. I'm not saying that it's not useful, but the question here is that sometimes we have to question ourselves. Do we really need to worry too much on every little things? Or not? Okay? So that's the lessons that we learn from these things. Okay? So this, I'm going to skip this. So I still have a bit to sum up what we learned so far. And that's the weighting functions. Now let me ask you the questions. When will this be more S-shaped? Meaning small probability becomes even more overweighted. Research say that it becomes more S-shaped for something that has an emotional attachment. Something that is called affect-rich items. So that example would be airplane crashes, emotional outcomes, disease deaths, and things like that. So for all things that have these affect-rich items, these decision weightings becomes more S-shaped. Okay? So that's the decision weighting. So the last one I come to. So to repeat, the first one is attitude towards gains and losses. Second is reference point. The third one is decision weighting. We put everything together, we get the value functions. So what is the value function here? In addition to that probability weighting function, and the shape of the value function is another important aspect that distinguishes prospect theory from expected utility. So because people have different attitudes towards gains and losses, and reference points matter. So for example, I'm gambling and losing. Getting back even may be my reference point. So the reference point could be anything. See, GPA 4.5 could be a reference point. Salary increase of 40%, where everybody get, is my reference point. Okay? So it suggests that the value function should have this kind of shape. There are two domains. We have gains domains, and we have losses domains, and we have that reference points, the one in the middle. Because people are risk-seeking in losses, it must be that in the loss domains, this value function has a convex shape. And because people are risk-averse in gains, in the gains domain, these value functions will have a concave shape. So different from the expected utility, where you have only one type of functions, either risk-averse or risk-seeking. Here, your attitude differ with regards to the domains. In the loss domains, you have risk-seeking attitude. In the gains domains, you have risk-averse attitudes. Okay? So typically, you write it down like that, so there is a coefficient of risk aversion parameter there. Okay? So I guess that's more or less putting everything together. So that's giving you a basic of prospect theory. And I hope to be able to go, me and Jack, look at some example of applications that have an element of this prospect theory using reference point for environmental or energy related topics. Okay? So I have some little slide here. So maybe I'm going to, well, maybe I can continue a bit for 4 minutes, and then I'll give the time to Jack. So another violation of expected utility is something called ambiguity aversion. People don't like ambiguity. I don't like ambiguity. Things that are ambiguous, I don't really like. Okay? So there is something called Ellsberg paradox. have you heard about Ellsberg paradox? By the way, there is a movie called The Post, played by Meryl Streep. So the story is about the leakage of all the documents about Vietnam Wars, implicating all of the U.S. presidents from Eisenhower's, Truman's, all the way to Nixon. Okay, and you know, there is one person who actually got access to all of these documents and leaked out to the press. And you know that person? That person is Daniel Ellsberg. So Daniel Ellsberg from the Ellsberg paradox. Okay, so so this Ellsberg paradox shows violation of the expected utility theory. So people dislike ambiguity. So that is, the devil you know is still better than the devil you don't know. So the experiment goes like this, and then I'll stop after that. There are two urns A and B, or 1 and 2. And there are blue and red balls inside the urn, like this. See, this is the first urn, 50 blue balls, 50 red balls. Second urn, blue and red balls, but you do not know the composition of blue and red balls. But the sums is the same, 100. But you just don't know how many blue and how many reds. Suppose that I ask you to choose. Would you rather bet on a blue drawn from urn 1 or a blue drawn from urn 2? Which one would you choose? What about this? A blue drawn from urn 2 or a red, sorry, so the first one is a blue drawn from urn 1 or a red drawn from urn 1. Sorry, the first one is both from urn 1. So what would you choose? You say, well, I know there are 50 blue and 50 red. Whether I choose blue or red doesn't really matter. So 50-50. So people would be indifferent between this. What about this? A blue drawn from urn 2 or a red drawn from urn 2? You think, I don't know how many blue there, how many red there. Okay? Because I don't know, I don't have to think too much about this. I'm indifferent between a blue drawn from urn 2 and a red drawn from urn 2. What about this? A blue drawn from urn 1 or a blue drawn from urn 2? And here, people usually think, oh, I know there's 50 blue, 50 red here, but I do not know how many blue there. I would prefer to choose urn 1. What about this? A red drawn from urn 1 or a red drawn from urn 2? Urn 1, because I know there's 50 red and 50 blue, and this one I do not know. So typically, the answer would be something like this. I am indifferent between this and this. I'm indifferent between this and this, but I prefer blue here than blue there, and prefer red here than red there. So that's the typical choice. But this violates the basic principle of probability. Why? Because if I choose B here, blue here, rather than blue there, I must think implicitly at the back of my mind that there are more blue here than more blue there. If there are more blue here, sorry, if there are more blue here than there, so this blue should be less than 50, and there should be more red because the sum is 100. So using the same arguments, when I'm asked to choose between 50 red here or red there, I should choose urn 2. Because probability must sum up to 1. Okay? So, since subject prefer to choose urn 1 rather than urn 2 in choice C, betting on blue balls, it must be, correctly or wrongly, she thinks that urn 2 has more red balls than blue balls. But if this is the case, they should choose urn 2 and not urn 1 in choice D. So because she thinks, correctly or wrongly, that urn 2 has more red balls. But people don't do that. the violations of the expected utility theory in the sense. So that's because of ambiguity aversions. Something that's ambiguous, something that I'm not quite sure, I'm going to stay away from that. Okay, so I'll stop here, and I'll give it to Jack.
Let me start by just, sorry. Was it? Yes. That's how I usually fix things too. Right. Okay. Let me just finish up a couple of more of those examples that I was talking about before of sort of violations of standard theory that have at least potential policy implications. One is the power of default. Default is a very strong motive. People hate to move from a default. Default, later we're going to talk about how people hate losses much more than they value gains. A default has a power in part because of that. In other words, if this is the default option, then I've got to change, which means giving up something which I really hate to give up to get something, and I don't really value getting stuff. So I tend to stick with the default. So a few examples of that is, one is an important one in many ways. That's donations of organs. Now there are two kinds of donations in a sense. One is from people who have died, and the other is live donations. Kidneys, for example, it's not common, but it's a lot of people who are living can donate a kidney to another person and continue living. It doesn't kill them or anything like that because you have two kidneys. And the other is after you die, then usually this is after an accidental death or something like this, that people donate after they've died. Now, in many countries, you have to sign something to say that that's okay. If I'm killed, you can take my kidneys, you can take anything you want, basically. Or you can designate, actually, in most countries, which things you are willing to have them take after you die and which things you don't want them to take. Why you would distinguish, I'm not sure, but it's up to you to do that. And the other is, in many countries, you are assumed to agree unless you sign something that says, no, don't do it. Now, in practice, okay, so then they ask, in countries where you have an opt-in, that is, you have to give permission, less than 20, typically something like 20% agree. People just don't do it, because the default is not doing it. So if I want to donate whatever, then I have to make a conscious change to sign up thing and give it. And on the other, I'm assumed to agree unless I opt out. And in those countries, European countries, Singapore has that option. In Canada, U.S., and many other countries, it's the other way. Different countries do it differently. People agree, don't opt out, basically. So the power of default is that strong. Now, in reality, the numbers don't sort of play out that way, because what happens is someone dies in an accident, for example, and has given permission to take for people to take the organs. What happens is then they ask the family, and the family often says, no, don't do it. And authorities are very, very reluctant to go against the wishes of the families. So in reality, these numbers don't hold up that way because it just doesn't happen because of the intervention of the families. So, and the medical people are willing to, do, and understandably so. If the family doesn't want them to do it, even though the person has already signed something, say do it, they won't do it if the family has any hesitation about that. So that's one of the problems. But they run surveys in which they say, do you think it's a good idea to have people donate their organs after death? And in most countries, big numbers, 70, 80, 90% kind of people agree, yeah, that's a good idea. Because there's a very acute problem of shortage of organs. So there are a lot of people who die in countries all over the world waiting for a new kidney, a new whatever, liver or whatever. There just aren't enough organs to go around kind of thing. So, people see that as a serious problem. So they say, yeah, we ought to encourage people to donate organs. But yet we find that it doesn't happen. But the opt-in, opt-out does change the numbers a lot, just not quite 80 to 20 kind of thing. It also affects. There were 2 states in the U.S. which offered automobile insurance through the state insurance agency, New Jersey and Pennsylvania. They were basically offered 2 options, and the 2 options were almost identical in the 2 states. And somebody got a hold of the numbers, and in New Jersey, the default, if you didn't opt out, was a cheap policy with some limitations on the coverage that you got on the automobile insurance. In Pennsylvania, the other was the default. It was more expensive, but had broader coverage. It was easy to change. All you had to do was to say, okay, no, check a box. I want to change to the other one, not the default. If I didn't do anything, I got the default. I had to pay that much. If I wanted to change, I checked it and just gave a bigger sum of money. And this is usually hundreds of dollars, if not thousands of dollars. It's not a $5 coffee mug. This is real money. And people, ought to pay attention on the thing. And what they found was that in New Jersey, 80% of the people ended up with the cheap one, and in Pennsylvania, 75% of the people ended up with the expensive one. In other words, the power of the default was enormous, even though a lot of money was at stake. And this is a serious thing that people should have thought about. But the default is that powerful. They're doing a lot now in different countries, European countries. The U.S. is spending a lot of effort on it. People basically are not providing for their retirement they're not setting aside enough money. They're not saving enough money for their retirement, and their standard of living is going to drop as a result of that. So socially, this is viewed as quite a serious problem. So there are quite a few studies now going on, and one of the things they're looking at is the power of the default. That many people get their retirement scheme through their employment. So when they go to work, I was talking about this earlier in that one case, they give the information that you have to opt in. they say, okay, this is the retirement scheme, you put in this much money, you get this much money when you retire, and so forth and so on. And they lay out the thing, and they say, do you want to sign up? The other is, you go to work, and they say, this is our retirement scheme, you're in it, this is how much you're going to be charged to contribute, this is what you're going to get when you retire, and so forth and so on. If you like, you opt out. And you see the difference in terms of the default. If the default is you're enrolled unless you opt out, most people stay in. If they have to join, most people stay out. So this is an important policy variable, is how can you, in effect, change the scheme so that more people end up enrolling, and the obvious thing is make the default that they're in. Because people just don't opt out, basically, is what is going on. This is an interesting example of another one called anchoring. And when I started working in this area, I just couldn't believe the numbers I was seeing on this phenomenon that we refer to as anchoring. An anchor is something that suggests a number that influences you to say another number that's totally unrelated to what the anchor was about. So if you are told something with the number 3, that influences you to pick the third one of something else, or something like that. In other words, the anchor. And the anchor can be really bizarre kind of thing. Now, to give you an example of an experiment that I found pretty bizarre, but also pretty striking. This was the one done in an MBA class, I think at Northwestern University, but I'm not sure of that. What they did, okay, these are people who, they're MBA students, they're supposedly reasonably intelligent people, so that's not the issue here. So what they said is, okay, pull out your Social Security card. Everyone that works in the U.S. has a Social Security card. It has a number, their Social Security number. It's a random number. Sorry, the last 2 digits are random. There's no significance to any of the digits. So they say, write down the last 2 digits of your Social Security number. So they're random numbers, and they relate to nothing. Then they said, okay, we're going to offer you a series of goods that you can buy. Tell us how much you're willing to pay for each one of these goods. And the goods were, sort of common things. A cordless, this is some years ago, so a cordless mouse, a cordless keyboard, a book, a box of chocolates, a bottle of wine, an ordinary bottle of wine, and a good bottle of wine. Define. Those are the items. So they asked these people, how much would you pay for the mouse and so forth? And they had it rigged in such a way that they got actual exchange. They actually got the wine or the book or the whatever, but it was rigged in such a way that only certain numbers you got the wine or whatever the item was. So there was an incentive to bid as much as they valued the good. What was surprising was that the numbers that people bid were very closely related to the last 2 digits on their Social Security number. They have nothing whatsoever, and transparently so, to do with each other, right? So the people with numbers that ended in 2 numbers from 0 to 19, they did on average for all of these goods $11.25. And as the numbers on the last 2 numbers increased, their bids increased. That's an anchor. That's how powerful an anchor is. They write down a number, and that influences how much they're willing to pay for a bottle of wine. As I said, when I first started working on this and saw some of this data on anchoring, I just couldn't believe it. I mean, people aren't that dumb, was my reaction. So I started doing my own. They are. And I probably am too. We fall for these anchors. They could be totally unrelated, like this. And they still have an influence on people's behavior. And it's consistent. So if you want to, get people to bid high, bid low, you can just drag them all over the place with an anchor. It's, anyway, it's far, far more compelling than I thought. The thing that, just to give an example of what Echo was talking about, in terms of the small probability, that the probability influencing decisions or the outcome influencing decisions. And the general sort of pattern is that things like wrongdoing, cheating on taxes, criminal activity, things like that, that the people who engage in those activities, they tend to worry and focus on the probability of getting caught. They tend not to worry about how long what the punishment is if they get caught. They tend to worry only about the chances of getting caught. So they look at the probability. And the example that Echo used before, things like environmental catastrophes, medical outcomes, and things like that, for some reason people focus on the outcome and they don't worry about the probability. And that is, as Echo sort of indicated, some direct policy implications in the sense of it's usually very, very expensive to change the probability, these things like medical and environmental, to change from 0.02 to 0.04 may be very, very expensive, or go the other way around, to avoid the thing. Going from 4 to 2 may be very, very expensive. And people really can't tell the difference. They don't focus on they only worry about the fact that we're talking about a nuclear meltdown or whatever the issue is, or a serious medical outcome. They worry about that. They don't really pay attention to the probability. So you as a planner, how are you going to handle this? You can go with the cheap option and people really don't care because they're not focused on the probability. Is that really what you want to do? It messes things up. And the probability of sanctions in terms of criminal activity. Now, economists, when you ask economists, sort of standard theory says, okay, if you want to cut down criminal activity, you can either hire more police or people to catch people, or you can lengthen the sentence, the jail time, incarceration time, or whatever the punishment is. That the economist says, okay, what potential criminals do is look at the expected outcome. They weight the probability and the sanction equally. They just look at the expected outcome. If I rob the bank, this is my expected penalty. It looks like a good deal, so they go rob the bank, kind of thing. You know, they make that calculation, supposedly. But in fact, that's not what people do. In the case of the criminals, they just look at the probability, and they don't care so much about the sanction. So in terms of public policy, if they followed the advice of economists, they would pick whichever is cheaper. Is it cheaper to hire more police, or is it cheaper to build more jails and make people serve longer sentences? So that would be the calculation. But if we look at what criminals really do, we would they worry about the probability, so we'd hire more police. Not worry about the sanction, because it doesn't really affect their decision. And that, by the way, is something that's been around for a long time. This is a quote from somebody in 1764. Crimes are more effectively prevented by the certainty than the severity of punishment. So they were already aware of it way back then, the criminals. And here, just more recently, saying the same thing. A 1% increase in probability is going to have much more deterrent effect than 1% increase in the severity of punishment. So these are just more of the kind of things that once we sort of figure out what's going on, then we can sort of respond in terms of how we want to form public policy, what kind of sanctions we want, or whatever. So that, making the link between knowing what people do and why they do it gives you a better clue as to what to do about it. So if you really want to, stop people from criminal activity, do this, not that. This is sort of the side. Okay, what I want to sort of turn to now, but I think we'll just break for lunch instead, is to get on to the thing that's ECHO, in a sense, started with what's called the endowment effect. And that's the difference between the value that people place on losses versus the value they place on otherwise equivalent commensurate gains. The endowment effect is a name that Richard Thaler gave to this phenomenon. He and I have had a running argument. I think it's a terrible name because it suggests that the endowment is some sort of legal entitlement. And what we're learning is it has really nothing to do with legal entitlement. It's a feeling of sort of psychological ownership or something like that. And so I think he's sort of biased our view of this phenomenon by calling it the endowment effect. But it's been known as the endowment effect for so long that it's not going to change. So we're going to call it the endowment effect too, in spite of the fact it's really a reference effect. But it's, and that's what he should have called it, but it's now called the endowment effect, and we'll get into that after lunch. It's probably the most important, or certainly the most researched part of all of behavioral economics, I think. And it's the thing that sort of attracted me first to getting involved in behavioral economics, and it probably is still the most important part of it, I don't think. By the way, just a mention of how the field of behavioral, if it's a field, has grown over time. It's a relatively new area, and as I suggested, it really started in 1979 with the publication of that paper. Back then, I was doing some stuff in the area, I'll mention it later, and I probably personally knew maybe close to half of the people that were active in that field back then, in the early days, in the 70s and into the 80s. So and there are people all over the world, but I personally had met probably close to half. Now, I don't know anyone, essentially. That the field is so big now that, you know, no one knows very many of the people. Now, part of it is a lot of the people I used to know aren't with us anymore, but that aside, I just don't know that many. And it's because the field has grown. Has the field also grown in terms of influence and actual use? My feeling is probably different than most people's, including Echo's. I don't think so. But we'll talk about that this afternoon. So after lunch, how long's lunch? Okay, we'll reconvene at 2, and we'll start with the endowment gain loss stuff.